Hello, this is our pre-lab discussion for Module 2 in CHY 114. And so today we are continuing our investigation of the Green River and trying to determine whether the possible whether possibly the housing development at Site A or the textile mill at Site B is contributing to some of our algae growth and fish kill down here at Site C. And so if we sort of think back and look at where we're at with things now, in Module 1, we conducted an investigation of the dissolved solids within the river. We looked at TSS, the actual physical mass of solids per liter of water. We also looked at quantifying the clarity of the water in looking at turbidity. And so today we move on from looking at actual dissolved particles to now starting to focus in on the amount of ions that are present. And remember that ions are nothing more than charged particles. And so we're going to look at both conductivity and pH. Conductivity is a measure of a water sample's ability to conduct electricity. And so the amount of charged particles has a huge effect on that. The greater the number, the greater the amount of charged particles within a water sample, the more that sample is able to conduct electricity. And so if we are able to measure the ability of a sample to conduct electricity, then that will tell us the relative amount of those charged particles that are present. pH is a term that even if you haven't studied it much, you're probably at least familiar with it. And you know that pH measures the acidity or the alkalinity of a water sample. What you might not have looked at, depending on where you're at in lecture and what you've looked at in other science classes, is you might not know that pH actually is the measurement of a very specific ion. When we measure pH, we're measuring the concentration of an H+ ion. And so it's really sort of a specialized conductivity almost, where instead of looking at the total amount of charged particles, we're looking at one particular charged particle when we look at pH. If we think about some of the sources of ions in in the river, we're looking at things like fertilizers from the housing development. There are lots of chemicals such as ammonium nitrate, ammonium sulfate, calcium phosphate, potassium sulfate, just to name a few. But lots of different ionic salts that are in fertilizers that may be able to make their way either down through the soil structure, down through the soil columns, and come into the river that way, or even runoff. A lot of storm runoff, maybe, if we get direct runoff coming from roads and down lawns, that can sort of sweep its way into the river. When we look at possible things that could affect the pH, that could affect the acidity level in the river, the textile mill uses some strong acids directly in their manufacturing processes. And so nitric and sulfuric acid in particular are things that the textile mill uses that could possibly be making their way into the river. And if we think about the nature of acids, in fact, if we look at nitric acid and sulfuric acid, recall that both of those are strong acids, and our definition of strong acids is that it's any acid that will fully dissociate into its ions. And so if there are significant amounts of these acids present, then that can affect the conductivity as well by boosting our level of charged particles. And so these are some things, if we do find some high conductivity or high acidity levels looking at the pH, these are some things that we might want to think about. These are some of the possible sources of that sort of contamination. And so what are the impacts? What does it matter if we have a lot of ions in there? Some ions are what's known as limiting nutrients, especially in water systems, where if we get basically a limiting nutrient is any sort of nutrient that there's not enough of it sort of in the natural state, there's not enough of it in the system to lead to huge amounts of plant growth. And if we do get an influx of that nutrient, however, then we can get a lot of things growing, a lot of things, especially algae, suddenly starting to appear. This is something that basically anyone from Maine, if you're from Maine, you've seen this in lakes and ponds in the summertime sometimes. If you suddenly see a lot of algae just appearing in the pond, then quite often, especially phosphates, are one of these limiting nutrients that midway through the summer, we start getting a lot of phosphates coming in through fertilizers and other sources like that. Now suddenly the algae has all of the nutrients that it needs to really have an explosion of growth. And so if we start to get high concentrations of some of these ions, then that's something that can lead to this excess algae growth that we're seeing, for instance, at Site C. If you've looked into eutrophication at this point, and hopefully you have, then you also know that this excess algae growth can eventually lead to decreased dissolved oxygen levels. Dissolved oxygen is something that we will be directly measuring in Module 4, but one of the things that we want to be thinking about as we move through this semester and as we look at this project is, are there some links to some of these things that we're investigating? Are there maybe some cause and effect things going on? For instance, if we do happen to find some really low dissolved oxygen levels at one of the sites later on, can we possibly link that to some high conductivity levels in the river as well? And so all of these things, we're going to need to be considering some of these relationships as we move on through this project. pH, all life essentially has and all different forms of life have a different pH range that make life, that life is compatible in. And so aquatic life especially has a pH range really of, especially the aquatic life we're looking at in the Green River, really this range of about 6.5 to 8.5, this green shaded range here. And this is just a measure of pH that was taken along the Green River, going back a few years. You can see that there was a bit of a dip here in 2017. It could have been due to anything, but then we came back up again. If the pH of a water system is outside of this range for too long, then that can also start to drastically affect aquatic life. And so we like to get pH measurements because they are a good indicator of some overall water quality. And so we want to see what might be going on there. So looking more particularly at conductivity, when we measure conductivity, what we're actually measuring is what we call the reciprocal of resistance. And so that's just sort of a statement about how the probe works, the conductivity probe that we're going to be using. The conductivity probe actually measures resistance. It measures how much resistance there is to electrical flow over the probe. And so less resistance, the easier it is for electricity to move, the higher the conductivity values. And the units that we use for conductivity are microsiemens per centimeter. You see that here. Siemens are just an electrical unit. And so we'll be looking in units of microsiemens per centimeter. In order to measure conductivity, we use a conductivity probe. And sorry, that word should say probe there as opposed to meter. But we're going to use a conductivity probe. And this conductivity probe has to be calibrated in a very similar manner to how you calibrated your turbidity meters. You are going to have a couple of standards, a couple of conductivity standards that you're going to use. And just like when we calibrated our turbidity meters, what you need to do is just make sure that you're following the directions on the card at your lab station very, very carefully. And so when you're following those instructions, remember what you're doing is you're using a couple of known standards. One of them will just be distilled water, which will have a conductivity level of 0. Then you're going to have another known standard. And then internally, the software creates a line of those points. And then in that way, we'll be able to use that information so that you can put the probe into your samples and your other conductivity measurements later on. You'll be able to just put your probe in there, and log a probe, the software will tell you what that conductivity is. So a couple things to note just when you're using the probe. Let's actually go to the next slide, which has some pictures of the probe here. So here's the conductivity probe that you're going to be using. It's just a Vernier conductivity probe, looks like this. So one thing to note when you're using this probe is that this bulb here must be fully immersed in your sample. And so just make sure you have enough sample and whatever you're using in order to measure, whatever glassware you have the sample in, has enough sample in it and is deep enough so that this bulb here will be fully immersed down into the sample. You also want to make sure that you're just rinsing the probe off in between each measurement. Easiest way that I've usually found to do that is literally just have a beaker sitting right at your station, and you can just put the probe sort of down into the beaker, and then just take you'll have your squirt bottle. You just squirt bottle, just rinse the whole thing off as it sits in that beaker. And then take a Kim wipe and just sort of blot the probe dry. You don't want to wipe it, that'll risk scratching the probe and scratching that bulb inside. But just blot the underside and blot around that probe a little bit to dry after you rinse it off. And you just want to make sure to rinse that very thoroughly in between samples so we don't risk any sort of cross-contamination. But again, similar to when you did turbidity, as long as you calibrate everything properly, you'll be able to get your conductivity measurements in that lower left-hand side of Logger Pro. It will display your conductivity for you. And so this lab in general, along with measuring our Green River samples, we're also just going to explore some basic ideas of conductivity, some of the basic concepts around conductivity. And so a few things that we have to sort of keep in mind is when we dissolve an ionic salt, when an ionic salt dissolves into water, remember it splits up into its ions. One of the things that we have to think about, though, when we're measuring conductivity is how many ions is that ionic salt going to separate into? And so, sorry about that. So let's just take a peek at a couple of these examples here. And so, for instance, NaCl. When we look at NaCl separating up into its ions, and we can see it on the slide, we're just going to sort of rewrite them here to really explore this. But NaCl as a solid, we then dissolve that into water, and that's going to split up into Na1+. So now it's dissolved in water, it's aqueous, and Cl1-. And so NaCl splits into 2 ions. And then likewise, calcium carbonate, so K2CO3. As a solid, we dissolve that into water, and now we've got 2 potassiums in our chemical formula. And so that's going to split up into 2 K pluses and our carbonate polyatomic ion. So K2CO3 is going to now split up into 3 different ions. And so let's say we have an equal number of moles of each. We take one sample or one container where we dissolve 1 mole of NaCl. That means that we're going to have 1 mole of Na in there and 1 mole of Cl-. But now let's say we also take 1 mole of K2CO3 and we dissolve that in water. We're going to have 2 moles of K+ and 1 mole of CO3 2-. So we would have a total of 3 moles dissolved in water. Even though we started with 1 mole of each, we end up with a differing number of moles of ions. And so we need to consider how something like that is going to affect our conductivity. If we have equal concentrations of 2 things, but those 2 things split into differing numbers of ions, how is that going to impact our conductivity? We also have to think about what a molecular substance will do if we put that into water. So in this example, we have table sugar, C12H22O11. We dissolve that into water. So this is now a molecular substance, all covalent, all nonmetals. Nonmetals are not made up of ions, or covalent substances like this made of nonmetals are not made up of ions. There's no ions for this to split into. And so we would still write this as all together, C6H22O11, but now aqueous dissolved in water, but there are no ions there. And so that's another thing we're going to look at is if we dissolve an ionic substance, or we dissolve a molecular substance, a substance that's bonded together covalently, what does that mean for the conductivity? Another thing we're going to explore is the effect of concentration on conductivity. And so if we just sort of think about that one a little bit, higher concentrations of a substance should lead to higher concentrations of our ions. And so we would expect possibly higher conductivity values. But we're going to look at that. We're going to actually explore that, doing some dilutions, and see if that is a relationship that holds true for us. Lastly, with conductivity, we're also going to explore what happens in a precipitation reaction and what is the effect of that on conductivity. So we have an example here of silver nitrate combined with sodium chloride, and we use our solubility rules, and we see that one of our new combinations, the silver chloride, precipitates out as a solid. And then we have aqueous NaNO3. And so, sorry about that. I just paused my video because I noticed that I didn't have aqueous written for my NaNO3, and I wanted to fix that. And so this reaction results then in the precipitation of silver chloride. And so we want to think about what effect something precipitating out will have on our ions as well. And so to do that, let's just take a look at our ionic equation for this reaction. So we have silver nitrate, aqueous, plus our sodium chloride, aqueous. We use our solubility rules, and we see that one of our combinations, our silver chloride, is solid, and our other combination, our NaNO3, is aqueous. And so let's first think about what this looks like before we mix these together. So let's look at our ionic equation for our reactants. So in one container, we would have a mixture of silver ions and NO3 minus ions. So those are in one beaker. And that we could measure the conductivity of that. It would have whatever its conductivity is. In another beaker, we have our Na plus ions and our Cl minus ions. So remember, that's what actually exists in our beakers. We've dissolved these in water, and so the ions have dissociated. So in one beaker, we have our silver ions and our NO3 ions floating around. In our other beaker, we have our sodium ions and our chloride ions. Those are all floating around. And so those would have whatever they might have for a conductivity value. Now, if we mix the two of these together, now let's not even think about the solid yet. We mix the two of these together. And so now we've got all four of these ions floating around in this solution. And so there are other things sort of at play, so it doesn't work exactly like this. But we would think, just for simplicity's sake, we would think then that the resulting conductivity of the mixture is a result of all four of those ions floating around. And so we would expect that possibly the conductivity would be the sum of what the two of them were separately. But so that's what we're going to look at, because what we see, remember, is that we actually end up forming a solid. And then we also still have running out of space, but remember, both of those are aqueous as well. So we form our solid, and we also have our Na and our NO3 ions. And so in our resulting mixture, only two of these four are still in the ionic form. The other two are now clumped together as a solid, no longer ions. And so we would expect that to have a role to play in the conductivity of the entire mixture. And so that's another idea of another concept of conductivity that you're going to explore in this lab, is by taking the conductivities of a couple mixtures, mixing them together, precipitation reaction will occur, and then you're going to look at what the conductivity is of the actual mixture. pH. So again, most of you are at least somewhat familiar with the concept of pH. You've seen it before, probably were introduced to it the first time in maybe even an elementary school science course. I remember that our pH scale is between 0 and 14. Anything on that scale that's below 7 is considered acidic. Anything on the scale above 7 is considered basic. Anything that is right at 7 is considered neutral. Like I mentioned earlier, pH is a measure of our concentration of our H plus ions. And so this is how we actually calculate it, is that pH is the negative log of H plus. If you haven't seen these brackets yet, these brackets just mean molarity. And so pH is the negative log of the molarity of our H plus. If you're not familiar with logs, if you haven't seen logs in other math classes or science classes, don't worry about it too much. We're not going to be delving too much into the actual math of this. You just need to know that this is, for one, that this is how we calculate it. For another thing, recognize that pH is a log scale. So this log, this really means that we're looking at factors of 10. What this means for pH is that a difference in 1 pH unit is actually equal to a 10-fold difference in hydrogen ion concentration. And so what that would mean is that if we have a solution that has a pH of 2, that solution is actually 1,000 times more acidic, 10 to the third, than a solution with a pH of 5. And so that's just something to really keep in mind whenever you're thinking about pH. It's one thing to say, oh, it's only a difference of 2 pH units. That's not much of a difference. Well, that difference of 2 pH units actually represents a 100-fold difference in the actual H plus, a 100-fold difference in the acidity. And so that's just something to always keep in mind, is that every move you make in the pH scale, you're actually moving the decimal point by a full place. It's a 10-fold difference, an entire order of magnitude. So always keep that in mind whenever you're working with pH or thinking about pH. Okay, let's take a look. So again, at how you're going to measure pH. You're going to measure pH in the very, very similar way to how you measured conductivity. You're going to be using a pH probe. It's pretty much used in exactly the same way that the conductivity probe is. You calibrate it in a very similar manner. You'll have a couple of different pH solutions at your stations, probably a pH 4 and a pH 7. And you go through the same exact sort of steps. Again, make sure that you follow the steps on your card at your station just very carefully, and you can't go wrong. But within Logger Pro, you'll go to experiment, calibrate, pH, and then you'll go through the same exact steps where you'll have your pH 4, I think it is, put your probe down into that, type 4 and keep, and so on. Again, just follow those directions. Same thing, making sure to rinse to make sure that bulb on the pH probe is fully immersed, making sure to rinse that probe very thoroughly in between samples. The big difference is that when you're not using your pH probe, put it back into the ionic solution that it's in when you first come to lab. pH probes, if they are not left in an ionic solution for too long, they end up essentially going bad, for lack of a better term. And so they need to stay in an ionic solution. Now that doesn't mean that you have to, that it can't stay out for 10 seconds and then you've got to slide it right back in, or the whole thing's gonna just go. You've got a little bit of time. It just can't stay out for long periods of time. And so you just have to be aware of that. And so that's just a good idea to get into the habit of with a pH probe. It's just whenever you're not directly measuring, just put it back into that solution. And so you're going to do a couple different explorations with pH. You're going to explore the pH of some various household substances. You're also going to explore the effect of a buffer on a water system. Now, this is one that honestly, this semester, recording this now for the fall 2020, that we're not going to have time to do in lab. And if I reuse the same video for spring 2020 or spring 2021, same thing. We're not going to actually be able to explore this titration in the lab, or this buffer in the lab, but you're going to receive some data for it. And so that's another thing that we are going to explore, is what effect does something called a buffer have on acidity values. And then we're going to, like I said, look at the pH of some various household substances, just to sort of get an idea for things, to get an idea for, just how acidic is some orange juice, how acidic is soda, how acidic, and what's the pH of things like bleach or some household cleaners, just to get an idea of pH levels of things that we see and use every day. Let's talk for a few minutes about the solutions that you're going to make. And so again, for the sake of this experiment for this semester, with the time constraints that we have and looking at the lab skills that we want you to develop, so obviously taking our measurements, using our probes in order to measure conductivity and pH, that's one of the lab skills that we focus on this week. Another big lab skill in general, though, is simply being able to make solutions, and being able to make solutions of specific molarities and specific concentrations. And so solutions will have to be made up quite often, either from a solid, so we'll have some of the solid in a container sitting in our stock room, and then we have to make up maybe 0.02, a certain amount, like this example, 0.025 molar, make up 100 milliliters of that. We also have situations where we have a stock solution. So we have a solution, and then we also have to make a certain amount at a certain molarity of that solution. And so that's the other big skill that this lab is focusing in on, is your ability to actually make solutions. This is something that's done all the time. Our lab aide, Lee, who does a great job for us in preparing solutions for you guys and getting everything ready for lab, this is one of the main things that she has to do on a weekly basis, on a daily basis sometimes, is making a certain amount of a certain concentration, a certain molarity solution. And so this is a big lab skill to have. And so again, sort of with the interest of time, we're going to have you focus in on making one of these solutions, and the rest of the solutions for today are going to be provided for you. But what you're going to need to do first, so you're going to focus in on making your 100 milliliters of 0.025 molar ammonium nitrate. And so hopefully you've done some of these already, but let's take a look at the calculations that you need in order to make up a solution like this. And so we need to make 0.025 molar, and we need to make 100 milliliters of that solution. And so if we think about what you need to actually physically do, so you're going to make the solution. You're going to make 100 milliliters of 0.025 molar ammonium nitrate. And so, and that'll be in a solid. It's going to be in its solid form at your station. And so the thing that you need to know in order to be able to physically do this, you need to know what mass of ammonium nitrate do I need in order to then add this into my glassware and get my liquid level up to 100 milliliters. And so that's the information that you need to have. Physically, what mass of ammonium nitrate do I need to weigh out to add that into my glassware? And so let's think about what that calculation looks like. So we've seen this in lecture. This shouldn't be anything new. So again, we're looking at preparing, where we want to prepare 100 milliliters of 0.025 molar ammonium nitrate. The way that I would start this calculation is our given information is our 100 milliliters. That's what we're starting with. We know that molarity is in terms of liters, and so we need to convert that. So 1 liter per 1,000 milliliters. I would then use molarity. Let's get rid of liters and convert this over to moles, because we remember that the units of molarity, so 0.025 moles per 1 liter. And so if I stopped right now, this would tell me how many moles of ammonium nitrate that I need to weigh out. We don't have a balance that measures in moles. We have a balance that measures in grams. So how do we convert between moles and grams? We use our molar mass. The molar mass of ammonium nitrate, 80.043 grams per mole. And so we plug this into our calculator. And we get 0.200 grams of NH4NO3. So there it is. I like to have you guys do calculations on your own, but this was a good one to start out with to show you. this is the actual amount that you're going to use. You need to measure out 0.200 grams of ammonium nitrate, put that into your container, into your volumetric flask, and then raise the liquid level up to 100 milliliters. And after you've done that, you will now have 0.025 molar NaO or NH4NO3. And so that's making a solution from our solid. Even though you're not going to make them yourselves, your pre-lab does have you doing the same exact calculation for all the other solids. And so make sure that you know how to do those, that you can work through your pre-lab to find that information. Just make sure that you are looking carefully at the different volumes, because there are different volumes for some of those, looking on page 43 of your pre-lab. And so those will be some different calculations. And so now what you're going to do is, so we have this 0.025 molar ammonium nitrate. You're now going to make several different solutions from this 0.025. You're going to make a 0.20, a 0.015, and a 0.10 molar solution. And you're going to make all of these from this 0.025 molar that you just made. I'll show you how to do the calculation for the first one. And for each of these, you're going to make 25 milliliters. And so this is another calculation that we have seen before. Sorry, I'm just looking at something real quick in our procedure here. Well, this is another calculation that we have looked at before in lecture. This should look familiar. C1V1 equals C2V2, our dilution equation. And so again, thinking about physically what you're going to need to do, you need to know how much of the 0.025 molar to use to then take that amount and scale it up to your 25 milliliters so that you have the concentration that you're looking for. And so in our first case, we want to make, what we're actually looking for is our C2 and our V2, or what we're trying to make is our C2 and our V2. So we're trying to make a 0.020 molar, and we need to make 25 milliliters of that. Now remember, in our dilution equation, we don't necessarily have to work within liters as long as we're consistent. If we're working with milliliters on one side, the other side will be in milliliters as well. Our C1, that's what we're actually starting with. That's our 0.025 molar solution that we've already made. And so V1 is what we're looking to solve for. That's how much of that solution that we need. So we just do a little easy algebra to this. We see that V1 is equal to 20 milliliters. And so that tells us then that what I need to do is take 20 milliliters. I'll actually just write this out. So take 20 milliliters of the 0.025 molar that was previously made, and dilute that 20 milliliters, dilute with a U. Sorry, that's going to bug me if I don't fix it. Dilute up to a total of 25 milliliters. And then I'll have a 0.020 molar solution. And so then you'll just have to do the same thing in order to make your 0.015 and your 0.010 molar solutions. And then, like I said, the rest of the solutions for this experiment today are going to be made for you. You're going to have stock solutions of your CaCl2, your Na2CO3, your glucose, your C6H12O6, and your HCl. Those solutions will all be made for you. You're just going to be making your ammonium nitrate solution on your own. The rest will be made for you sitting at your station in order for you to get your conductivity measurements and do your mixture. As far as a mixture, you'll be mixing together some CaCl2 and some Na2CO3. That's the one that we're exploring for our precipitation exploration. So you'll get the conductivities of each of those separately and then mix them together and find the conductivity of the resulting solution. Again, that's for the CaCl2 and the Na2CO3. So let's just sort of outline your tasks in this lab, because things are a little bit different from what's in your lab manual, again, just because of some of the changes that we are making due to this semester and our time constraints. For one, remember we're putting task 1 and task 2 together. You're doing both conductivity and pH today. You're doing the whole lab combined. And so if we outline the tasks that you need to do, you need to first make your NH4NO3 stock solution from the solid, and that is 100 milliliters of the 0.025 molar. That's your first task. You then need to use your dilution equation to make 25 milliliters each of the 0.020, 0.015, and 0.010 molar NH4NO3 solutions. And then you need to find the conductivity of all of those solutions. And so you'll have 5 different solutions at this point: 0.025, 0.020, 0.015, and 0.010. Find the conductivity of all these NH4NO3 solutions. You will also have to, should use the word measure instead of find to be more scientific-like, but you're going to then measure the conductivity of your CaCl2 solution, Na2CO3 solution, C6H12O6 solution, and your HCl solution. So those are, again, already made for you. You just need to measure the conductivities of those. Mix together some of the CaCl2, the calcium chloride, and the Na2CO3, the sodium carbonate. Mix those together. Measure your conductivity of the mixture. And then lastly, Green River project. Measure the conductivity of all of your Green River samples. And so you're going to get these conductivity values. And then moving on to pH. So these are all of your conductivity tasks. Moving on to pH, some fewer tasks that we're going to do, which are going to measure the pH of the household solutions that are at your station. And then also measure the pH of your Green River samples. And so those are all of the tasks that we are looking at doing in this lab. When you are measuring the conductivity and the pH, it's similar to when you measure turbidity. You're not going to have a point where the probe just settles in right directly on a measurement and stays there and stays steady. You're going to have to watch it and sort of see and recognize, okay, it's pretty much staying right around this value now. And so my conductivity is this. So this is a lot. This is part of the reason why I'm sending out this pre-lab video ahead of time, so that you watch this video before we come to lab, and you're able to hopefully just sort of hit the ground running, come to lab and get right to work, because we've got a lot to do today. And so hopefully you are watching this before we come to lab, and you're ready to go once we get there. As always, ask me any questions that you have, or ask your instructor if another instructor is showing you my video. And then we should be able to get through everything just fine. And so that is the end of our pre-lab discussion. And so have a good lab and stay safe.